All right. Good afternoon, everybody. Hope you're doing well. We're going to continue on with our lectures today, and we are going to talk about something called the second law of thermodynamics here in this lecture this afternoon. And this is a really cool mathematical statement. Ultimately, it's going to allow us to compute something called delta G, which is going to be the change in Gibbs free energy for a reaction. And this is going to allow us to predict whether or not the reaction will occur or proceed as written. And if it does, we call that a spontaneous process. And if it doesn't, we say that it's a non-spontaneous process. So here in this lecture, we're going to define what a spontaneous process is. We're going to review the first law of thermodynamics, which is something that you've already actually considered in a previous semester of chemistry, back in chapter 6. Talk about conservation of energy. That's the first law of thermodynamics. We'll refresh our memory here of enthalpy for reactions. And again, all that stuff was covered in General Chemistry 1 or 1307. That's all in chapter 6 of your book. So if you need to brush up on that, that's where you're going to find all of that content, okay, that reaction enthalpy bit, or delta H. We want to know that this thermodynamic bit that we're going to talk about considers only whether the reaction will or will not occur. It doesn't say how fast the reaction will occur. The rate of reaction is the domain of chemical kinetics. Of course, we considered that earlier in this semester, okay? So this thermodynamics business is different. It just says whether the reaction will occur or will not occur. But the reaction rate's the domain of kinetics, okay? We'll then do a relatively simple derivation for the second law of thermodynamics, which is going to allow us to come up with this equation for delta G, the Gibbs free energy change. Gibbs free energy is going to have the units of joules, but the power of this delta G variable is it tells us whether a reaction will occur. So it's actually quite interesting. And we're going to talk a little bit about enthalpy and entropy changes for a particular reaction and how that influences this value of delta G, how it influences the reaction's spontaneity. And then last but not least, we're going to practice using an equation to compute delta G. This equation, I think it's on your equation card that I gave you at the beginning of the semester, and you're definitely going to want to commit that one to memory because we're going to use it a lot to predict whether or not a reaction is spontaneous or non-spontaneous at a particular temperature. And it turns out that temperature is a variable in this equation. We're going to see a capital T, which is our Kelvin temperature. And believe it or not, the equation even allows us to predict what temperature a given reaction may become spontaneous at. In other words, if we heat up the system or cool it down, it might change the properties of the reaction. So we're going to get to that eventually here in this lecture. So it's actually really quite interesting. Okay, so let's just kind of dive in then and review a little bit. One thing I'd like you to remember, and I already said this, okay, is that this idea of chemical thermodynamics, it really predicts whether a process is going to occur or not. It doesn't say how fast the process will take or how slow it will take. It doesn't say that at all. In fact, if we look back on this first slide, I forgot to mention it, but I had this nice picture right here on the top. This picture is pretty interesting because what it is, if you look closely, is it's diamond, which is an allotrope of carbon, being converted to graphite, which is a different allotrope of carbon. Both of these substances are carbon, but of course their properties are very, very different. Their appearances are very different. I think we said last video that the diamond has carbon atoms which are linked. The layers are linked from top to bottom. You can see these little linkages in through there. Okay? But graphite does not have that. These little blue lines which are in this side are not really true linkages. There's just dispersion forces that exist between the carbon atoms, between these planes of atoms here in graphite. So these materials are very different. Graphite likes to come off in sheets, but diamond is very, very hard and it doesn't do that. Just so happens that the conversion of diamond to graphite is considered a spontaneous process. So if you have diamond jewelry, diamond rings, the idea is eventually that diamond's going to be converted just to simple graphite. But it occurs at such a slow rate, fortunately. This is not of much consequence to us in our lifetime. And in fact, you can pass that diamond ring through many generations, and it's not going to be a very prevalent process. You're not going to notice it because that reaction is so slow. But nonetheless, it's thermodynamically favored. So the key point then is that this thermodynamics just predicts whether the reaction will occur if given enough time or not. A process that will occur, like diamond forming graphite, is said to be spontaneous. That just means that it happens. It doesn't mean that it happens fast. It just happens. It's a spontaneous reaction. Okay? It's favored thermodynamically. On the other hand, non-spontaneous processes require energy input to force them to occur. They will not occur on their own under the set of conditions specified. This is a non-spontaneous process. So we have spontaneous, we have non-spontaneous. We really just want to know the definitions of those at this point, because later in this lecture, we're going to learn to predict whether a chemical reaction is spontaneous or not, okay? Now, how do we know whether a process is going to be spontaneous or not? Well, it turns out what we do eventually here is we're going to compare something called the chemical potential energy of the system. This is going to basically be metered or metric. The metric for this is going to be delta G, this Gibbs free energy change for a process. But we compare the chemical potential energy before and after the reaction and to see if its situation improves, okay? If the system after the reaction has less chemical potential energy than before, the reaction is going to be thermodynamically favorable and it's going to be spontaneous, okay? Again, spontaneity is not fast or slow, it's just whether the reaction will occur or not, okay? Now, way back when, in General Chemistry 1 or 1307, y'all actually were introduced to one of our laws of thermodynamics. It turns out there's going to be 3. But you've talked about one in Gen Chem 1, 1307 already, okay? And this is the law of conservation of energy. The first law of thermodynamics is that energy can't be created nor destroyed. The total energy of the universe can't change, it's a constant. Now we can transfer energy from one place to another, but we can't create it nor destroy it through our chemical processes. This is our first law statement for thermodynamics, okay? Now again, if you're having a hard time remembering this business, you talked about all that in chapter 6 of your textbook back in Chemistry 1307 or General Chemistry 1 here at Texas Tech, okay? So chapter 6, you might want to look at that. We will touch on some of the concepts there. So because of that, if you feel lost with this enthalpy bit, which is delta H, you can always go back to that chapter and it'll help you, okay? We aren't going to get into it too much, but at times you might need to kind of glance back there, okay? But nonetheless, this is our first law of thermodynamics, okay? Energy can't be created nor destroyed. We also learned in chapter 6 that for an exothermic reaction, now of course exothermic reactions, if you remember back to that business, we talked about enthalpy changes. These are the ones that had negative values for delta H. This is my triangle right here, okay? That's an exothermic reaction. In such a reaction, heat is lost from the system and goes into the surroundings. The reaction system feels warm to the touch. It feels warming up, okay? The reaction occurs and things get a little bit warm or hot. This is an exothermic reaction. The opposite is true of an endothermic reaction. It looks like I don't have that written on my slide here. I don't know how I forgot that. But an endothermic reaction is one in which the delta H is a positive value. That's my endothermic, positive value, okay? The endothermic reactions, those are the ones that it feels cool to the touch. You might mix some chemicals and all of a sudden the beaker gets really, really cold. And the reason why that is because in an endothermic reaction, heat flows into the chemical system from the surroundings. Now, if you're touching that and it's feeling cold, again, what's happening there is heat flows from your hand into the reaction system. All right, and that's actually, you're perceiving that as a coolness or a cold, okay? Now, there are two ways that energy is lost or transferred really between a system and its surroundings. Heat and work, Q and W. And last semester, again back in chapter 6, you learned a series of equations, such as these right here, to talk about energy flows or energy transfers. And you also learned that delta E, the change in internal energy for a system, is a state function. It doesn't matter how you get from point A to point B, but as long as you go from a very specific spot to a specific other spot, the delta E is conserved. You also learned that delta H is called the enthalpy change of a reaction, okay? Back to chapter 6. Now let's move back to thermodynamics and spontaneity of reactions for a second, okay? That was kind of a review of chapter 6. That's my point in doing that, okay? So if you want to think about these spontaneous processes and start to sort of rationalize whether or not a process will occur or not, you might think that spontaneous processes are all exothermic, right? Because what do we know about the natural world? And if you think about a ball on a hill, there's an incline or a hill down to the flat land here. That ball probably might spontaneously roll down that hill, right? Under the force of gravity. And in doing so, the ball lowers its potential energy. So if we're just going to sort of guess at what's important for spontaneous processes, we would probably guess that exothermic reactions are spontaneous. It turns out that some exothermic reactions are spontaneous, but that's not the only thing that's going to be at play. Now, remember that exothermic processes are the ones where energy is given off to the surroundings, right? Heat energy is given off to the surroundings. These are the ones with the delta H having a negative sign. The enthalpy of reaction is negative. It's exothermic. And that's actually good for chemical spontaneity, or helping reactions to occur. But as I mentioned, it's not the only thing that's important. And the reason why we know that is because there are some endothermic processes. This is the one where the enthalpy of reaction is a positive number. And here we have to put energy into the reaction system. So it's like the ball rolling uphill, so to speak, okay? And we know that some endothermic processes are spontaneous. Some go from a system of lower potential energy to a system of higher potential energy. So how do we explain that? How do we explain that? How do we explain that there are endothermic processes which will, in fact, be observed to occur spontaneously at certain temperatures? And it turns out that entropy, what we learned about last lecture, is the reason why this occurs. Entropy also is going to play a big role in making a process spontaneous or non-spontaneous. So it turns out that both enthalpy and entropy play crucial roles. And both of these changes in a given chemical reaction are important. And we're going to have to talk about both of them here, okay? When we're talking about spontaneous processes. So let's dive in a little bit deeper then. So factors affecting whether a reaction is spontaneous. We just said that both enthalpy, change of a reaction, and of course enthalpy, this one, is our delta H, triangle H, that's our enthalpy. And entropy is our delta S. We learned how to calculate that last lecture. That's our delta S, right? Let me see if I can draw a prettier S. So both the enthalpy and the entropy change are important. Now the enthalpy change, delta H, is the difference in the sum of the internal energy and PV work for the reactants compared to the products. Again, you learned to compute that back in chapter 6, okay? And if you're struggling with that a little bit, you can kind of go back in chapter 6. I think the most relevant area of chapter 6 for you to consider probably would be pages 375, maybe up to, oh no, that's 275, excuse me. Page 275 through really 280, just looking at my textbook here. I think 275 through page 280, there's a lot of calculation problems in there that explain how to compute enthalpy change, and that would be a good review if you forgot that, okay? But that's basically just telling us about the difference in the sum of internal energy and PV work products compared to reactants. Now, on the other hand, the entropy change, delta S, is what we learned about in the last video. It's really this difference in randomness of the reactants compared to the products, this ability to distribute energy throughout the molecules in our system, all right? So both of these things are important. So again, factor 1, enthalpy change, you learned about that in Gen Chem 1, chapter 6. It's usually measured, this delta H term, usually measured in kilojoules per mole. I want you to note that because that's going to be important later. It usually has kilojoules per mole units attached to it, okay? And this is basically a measure of the stability of the bonds products compared to reactants, okay? That's kind of what this is all about. And again, the second factor I just mentioned is entropy. Entropy is given the symbol S, and it's a thermodynamic function that increases as the number of energetically equivalent ways of arranging the molecules or the components within our sample increases. It usually has units of joules per mole Kelvin. So I just mentioned that delta H usually has units of kilojoules per mole. S usually has units of joules per mole Kelvin. Okay, now that's going to be important, and I want you to make note of that, because once we derive the equation for the second law of thermodynamics, we're going to plug variables in it for delta H and delta S for a reaction, as it turns out. You got to make sure that the units jive and the units are compatible. Usually what that involves is we're going to convert our delta H value into joules per mole, so that it agrees well with entropies, which are in joules per mole per Kelvin, okay? Now, last lecture we talked about entropy could be computed through this equation. We're not going to use that much, as it turns out. Instead, we are going to use the equation for the summation law that we learned about last time. But nonetheless, we're going to compute both entropy change and enthalpy changes for the reactions. Now, let's start to put the pieces together. It turns out that the natural world prefers the entropy of the universe to increase. And in words, what I just highlighted there is the second law of thermodynamics. Because if I was going to say that in slightly different language, I might say all spontaneous processes increase the entropy of the universe. And it turns out that that sentence right there governs our second law of thermodynamics. That's what the second law states mathematically in words. So what that means, if we think about it and reflect upon it for a second, is that any process which will increase the entropy of the universe will be spontaneous. So I like to say that nature prefers disorder, right? And it's kind of a funny joke that the teenager or the preteen might have a really messy bedroom or something like that. Their parent tells them to come clean up, and they say, "Oh, nature prefers a high entropy state," right? Yes, that would be a pretty intelligent, preteen. But you get the idea, right? Your room gets messy. You gotta dump a bunch of dirt all over your floor, and you gotta clean it up, so to speak, right? So I think we can all kind of identify with that to a um, certain point. But nonetheless, in words, that is what the second law of thermodynamics tells us. Okay. Now let us start then to draw some mathematical statements. And the first one that I'm going to write is the equation that I just highlighted. I wrote delta S universe, or the change in entropy of the universe. Now remember, that number has to be what? Positive if the process is going to be spontaneous. But how can I find that or define it? Well, it's nothing more than being equal to the entropy change for the system plus the entropy change for the surroundings. Now remember back to chapter 6, you talked about heat flows, and heat could be lost or gained by the system, and heat could be lost or gained by the surroundings. This is sort of the same concept here. If we're talking about an isolated reaction, chemical reaction inside of a container, that is the system. Now there might be an entropy change associated with that chemical system or that reaction, but that's not the universe. That's not everything that is present in the universe. That's only the system. So that's the reaction system. The surroundings then is everything else. So if I sum together the entropy change for the system and the surroundings, that tells me my delta S for my universe, okay? So if the entropy of my chemical system decreases, the entropy of the surroundings must increase by a larger amount for the process to be spontaneous. We have to consider both the system and the surroundings, and fortunately, that equation right there does that for us. So what are we going to do with that equation? Oops. Well, we're going to take the equation that we just spoke of, and I'm going to write it right here, okay? I highlighted it, it's right there. Delta S of the universe is delta S system plus delta S surroundings, okay? And now we're going to substitute into it. We're going to substitute in for this term right here. Because it just so happens that my delta S surroundings can be said to be equal to negative delta H system divided by T. Negative delta H system divided by T. So since this is equal to my delta S surroundings, or my entropy change in my surroundings, I'm simply going to take that and plug it into this equation as this arrow shows. Because of that negative sign, this positive becomes negative right there. And you have delta S universe is equal to delta S system minus delta H system divided by T. Now this is just a simple derivation or substitution into the equation because one thing is equal to the other, but it does something kind of powerful for us. Before the substitution, I was considering the enthalpy of my surroundings, wasn't I? Or the entropy of my surroundings. But after the substitution, I'm considering the enthalpy of the system. This second equation that I just derived through this simple substitution, this one right here, now describes whether the process is spontaneous or not through parameters only associated with the system, the reaction system. Everybody see that? So I now can use the enthalpy and entropy change associated with my reaction to start to say whether or not my delta S universe will increase or decrease, whether it will be positive or negative. And that's kind of the power of that equation, okay? Now we're going to be doing a little bit of other mathematical manipulations or cleaning up or just changing things a little bit here before we proceed. The first thing that we're going to do is we're going to multiply both sides by negative T, where T is the Kelvin temperature. So if I multiply both sides, on the left I get this statement. Negative T times delta S universe. Okay, because I multiply both sides by negative T, that's only changes that. Now on the right, I'm going to multiply this right side, the entire right side, by negative T. So it would be like drawing a parentheses around this, right? And then you got to distribute that negative T for both terms. So if you do that, you get negative T delta S system. But over here, what do we get? We get a plus H system. So what happened there? Well, let's see. We had a T in the denominator. So this T and this T are going to cancel each other out. And the negative make a positive, don't they? So sure enough, when we do the multiplication, we generate this equation right here. Now what we're going to do is we are going to give this term right here an alternate name. We're going to call it delta G. And it turns out that that alternate name, delta G, is called the Gibbs free energy change for a reaction. This is that change in the chemical potential energy that we were talking about earlier in the lecture. The Gibbs free energy change is our delta G. And it's nothing more than that term right there. The negative T delta S, okay? Now we're going to clean up the rest of the equation. This one was positive, wasn't it? Okay. So we're going to bring that down here, our delta H system, okay? And then likewise, we're going to take this minus T delta S, and we're going to bring that down here, minus T delta S system. But the beauty of this here, is we now have this equation for delta G, this change in Gibbs free energy. That's a relatively simple equation if you look at the form of it, right? It's the one that's in that red box right there. And that equation allows us to compute delta G for a system based upon the enthalpy change for that reaction system and the entropy change for that reaction system. So we're computing this number based upon, again, parameters for the reaction system itself. We don't have to worry about the surroundings or the universe anymore. We're just taking the system into account, and we can get this magic number delta G, the Gibbs free energy change, right? All right, well, let's think about the consequence of this for a second. On the previous slide, we learned about the second law of thermodynamics. And what did we say had to be the sign on delta S universe for something to be spontaneous? Didn't all spontaneous processes increase the entropy of the universe? So we want this number to be what? Positive in value if the process will be spontaneous. So what I'd like to do then now is just look right back here for a second. If delta S universe is positive, Kelvin temperatures can't be negative, can they? So what does that mean for us? Well, if delta G is negative, the reaction's going to be spontaneous. If delta G is a negative number, our reaction is going to be spontaneous. So we can use this equation to predict whether a reaction is spontaneous or not. And in addition, since there's a T built in over on the right here, that's our Kelvin temperature again, right here. If a reaction is non-spontaneous at one temperature, it might be spontaneous at a different temperature. And in some cases, we can rearrange this equation to solve for T, the temperature at which a process becomes spontaneous. So we can actually do a lot with this equation. And it's really cool, because by computing our delta G, we can figure out whether a reaction is spontaneous or not, and also what temperature range it might be spontaneous under. Now there's one word of warning, I guess, for using this equation that I want you to kind of remember. You gotta use consistent units when you're using this for calculations. I'm going to suggest that everybody uses joules of energy for both our delta S, which is kind of built in, and our delta H. Now this one's the one that's going to cause you trouble, the delta H. Because I mentioned earlier in this lecture that delta H term is usually in kilojoules per mole when you solve for it. Kilojoules per mole, or thousands of joules per mole. But this one, the delta S, is usually in joules, has joules associated with it, okay? So because of that, you're going to want to take the value for delta H system once you compute it or find it and convert it into joules, okay? If you don't do that, you're going to get the wrong answer for the magnitude of delta G, and things are going to be bad, all right? So convert to joules. That's going to be really, really, really important. I want to encourage you to do that. We'll see that in a sample problem here in a few minutes. All right, so let us then wrap our minds around all this, okay? We said on that previous slide that if delta G is a negative number, that makes a positive entropy change for our universe. That means the process will be spontaneous. It's going to happen. As the chemical process or reaction will happen as it's written. It's a spontaneous process. So let's thinking back to our equation here in red, the red box. How can we make this a negative number then? Well, let's think about it. There's a couple different ways, right? If delta H is a negative number, if our reaction is exothermic, and our delta S for the system is positive. So what happens? We run the reaction, the entropy increases, and it's also exothermic. Well, this is the best case scenario, isn't it? Because if this is positive, I multiply by the temperature and subtract it from a number which is already negative, I'm going to make the negative number bigger, or more negative, I should say. I'm going to make the negative number more negative. And as a result, in these cases, this is best case scenario. That's always going to be spontaneous, isn't it? What about an alternate case where delta H is negative and large, delta S is negative but small? Okay, now which of these is good for spontaneity, which is bad? Exothermic reactions, this delta H negative, that's good for spontaneity. But if my entropy change is negative, that's bad for spontaneity because my system's becoming less disordered, or I'm having less microstates to distribute my energy in when I run this reaction. That's usually not encouraged for spontaneity. But if we look back to the form of the equation, if delta S is a negative number, I'm taking a negative number for this and I'm multiplying it by a T. And then what am I doing? The negative and the negative makes a positive. I'm adding a positive number to my negative delta H. Now, if delta H is a large enough negative number or a significant enough negative number, the reaction can still be spontaneous because this first term, the delta H term, may overcome the second term. But you can see that in the second case now, these two variables are competing, aren't they? They're competing with one another. One's good for spontaneity, but the entropy change is bad for spontaneity, okay? There's other options. And what we're doing here basically, if we're having trouble following along, is we're just changing the signs of these variables, delta H and delta S, and we're seeing how that affects things, right? So another option is this one. Maybe delta H is positive, but delta S is a big number and positive. Now, which of these is good? Well, delta S being positive is a good thing because if our reaction increases the entropy, that's good for spontaneity. But this is an endothermic reaction, which is bad for spontaneity. So we take a positive number and subtract T delta S. Now, if delta S is large enough, I guess that we could say that this positive, or this contributing factor to spontaneity, could overcome this positive number in the mathematics. But delta T system, or delta S system better be pretty big, or else we better be operating at high temperatures to make that happen, okay, mathematically. So there's lots of different options, basically, okay? So this chart that's on the middle of the slide really works to summarize these things, okay? But the key idea is that we've got to make delta G in this equation negative, okay? That's a key principle here, okay? So let's think about all the options, okay? And again, this is not table 17, it's in table 20 in your book somewhere, okay? So let's say that we have an exothermic reaction that has a positive delta S. Entropy increases, it's exothermic. This is spontaneous in all cases. It's never non-spontaneous. This is our best case scenario, isn't it? On the other hand, what if you have an exothermic reaction, but entropy decreases? Which of these is good for spontaneity? Think about that for a second. Well, I like the fact that the reaction's exothermic, because that makes my delta H negative. That's more likely to make my delta G negative. But this negative sign here for my entropy change is a little bit of a problem, isn't it? If entropy decreases in my system, that's not good for spontaneity. So then, under what conditions is this likely to be a spontaneous process, and what conditions a non-spontaneous process? Well, let's think about if I'm operating the reaction at low temperature in such a case. Very, very low Kelvin temperatures. What's going to be the effect of that on my equation up here? Well, my T in the red boxed equation is going to be a small number. So when I multiply it by negative delta S, the product is going to be a little bit smaller than it would be at a higher temperature. So because of that, I'd be subtracting a smaller number, if you want to say that. Now, here, the sign on delta S is negative in this third case right here, right? It's a negative delta S. So when I take that negative delta S and I multiply by that small value of T, and then I consider this negative sign, it's like I'm adding this number in to my negative delta H. If I make this small enough, my negative delta H will be large enough to overcome it, or significant enough to overcome it, making my delta G still negative. So at low temperatures, this reaction might still be spontaneous. But at higher temperatures, what's going to happen is my T will take on larger and larger values in the equation, and that's going to eventually make this second term big enough to overcome the fact that the reaction was exothermic. And in that case, that's when the spontaneity of the reaction will stop. So here we have an example. If it's exothermic with a negative change in entropy, the reaction is going to be spontaneous at low temperatures and non-spontaneous at higher temperatures. Now, low and high, they're kind of arbitrary words, right? We don't know what's low, what's high. Maybe you have a different opinion than I do about what's low and high. But if we want to be specific and quantitative, we can always come back to this equation and solve for exactly what temperature we're talking about. Because once delta G flips signs from positive to negative or negative to positive, that's when we know we're at that crucial temperature, okay? All right, so if we're extending this to other possible cases, I guess we can think about the second case here, where the reaction is endothermic and entropy change is negative. Oh, this is really bad for spontaneity, isn't it? And this one's not going to be spontaneous at any temperature. If we've got an endothermic reaction, and also the entropy change goes down, man, you're going to have to do a lot of work to make that reaction even occur. This is a non-spontaneous case. So that's case number 2. What else do we have? Let's consider the last one. We have a positive and a positive side for delta H and delta S. So here we have an endothermic reaction, but at least the entropy change is favorable because entropy increases here. This is the case that will be non-spontaneous at low temperatures, but spontaneous at high temperatures. It's kind of the opposite of that one that we considered right above it, isn't it? See how these two kind of flip spots, right? So the moral of the story here is that this equation is kind of powerful for us because we can predict whether or not a given reaction will be spontaneous at higher or low temperatures, or whether it will be spontaneous at all. Another really important idea is that both entropy and enthalpy play a role for our reactions. And that's built into our equation, isn't it? We see terms for both delta H and delta S. Both of those things are important. Exothermic reactions are good for spontaneity of their reactions. Also, positive entropy changes are good for spontaneity, okay? So all those things we can kind of take away from this chart. So now let's practice a sample calculation based upon the things that we've learned here with this second law of thermodynamics. I want us to consider the combustion of propane gas. This molecule, C3H8, is propane. Okay, that's its formula. So you can go down to the Walmart or Market Street, United, and buy some of that in the tank, right, for your barbecue grill. That's what we're talking about. Now we're going to combust that. We know combustion reactions always take a fuel and add oxygen to make carbon dioxide and water. We see that form of the combustion reaction here. It's all gas phase reaction. And it looks like it's even balanced for us, isn't it? We're also fortunately told that the enthalpy of this reaction is negative 2044 kilojoules per mole of propane. This is our enthalpy, isn't it? That's the one from chapter 6. We can also see that this reaction is exothermic because of the negative sign. We probably already knew that because it's a combustion reaction. We're all familiar with combustion reactions giving off heat, all right? All right, so everything is about as expected. Part A, we want to calculate the entropy change in the surroundings associated with this reaction occurring at 25 degrees Celsius. Let's tackle that one. Now, how are we going to do this? Well, we need to go back to the equation that we learned a few slides ago. We didn't talk much about this equation, okay? But this was what we substituted into that entropy of the universe equation to derive that second law, the one for the Gibbs free energy. We said at one point that the entropy change to the surroundings was equal to the negative delta H reaction divided by the Kelvin temperature. So once we get there, this problem becomes pretty easy because all we need to do is plug and chug. Just have two numbers to plug into this equation and we're done, right? So what do? We plug in our reaction enthalpy. Notice that the sign came along. The negative 2044 kilojoules came along, right? The negative. And this negative sign is separate. So we have a negative and a negative. And we're going to divide by 298. Now why in the world did we have 298? Where did that come from? Well, we were told it was 25 Celsius. This temperature that's in the denominator must be in Kelvin. So all I did is I converted to Kelvin by adding 273. I forgot about the 0.15 here, right? So I just put in the 298, but y'all got that, right? No big deal there. And we just plug and chug. We solve for the answer. It's 6.86 kilojoules per degree Kelvin, which is 6.86 times 10 to the third joules per Kelvin. And that is our entropy change in our surroundings. Notice it's positive, okay? That's going to be important, I think, here in a second. So we can compute the entropy change in the surroundings. Now part B, determine the sign of the entropy change for the system. Now the system is what? It's this reaction, isn't it? It's that reaction, that's the system. We want to figure out what the sign of the entropy change is for that reaction. Well, how are we going to do that? We're not given any delta S0 values, but I think what we can do, since we only want the sign of the change, is think about the reaction sign. What do we have going on here? Remember in the last lecture we considered problems like this where we wanted to predict whether there was a negative or positive entropy change for the reaction. And we said that if we produce more moles of gas through carrying out the chemical process, that the entropy change was positive. Whereas if we produce fewer moles of gas, the entropy change would be negative. So I'm thinking about that principle, and I'm looking and I'm seeing that there's 3 and 4, that makes 7 moles of gas on my right side. And over here on the left, there's only what? 6. So through the chemical change of this reaction, I'm basically making 1 more mole. My delta N gas moles is +1, right? So I'm making more moles of gas throughout this process. That should lead to an ability to distribute my energy better. That's going to lead to a delta S for reaction. That's got to be a positive number. It's got to be positive because I'm making more moles of gas, aren't I? So my delta S system, okay, my delta S system is going to be a positive number. So my delta S surroundings is positive. My delta S system is also positive. Can I determine the sign on the entropy change for the universe? Sure. It's also going to be positive. And how do I know that? How do I know that? Because my delta S universe is what? Just the sum of my delta S system plus my delta S surroundings. And if the surroundings is positive and the systems is positive, I'm just adding 2 positive numbers together. I got to get a positive number here. So indeed, my delta S universe will also be positive. Now lastly, I'm asked if this reaction is spontaneous. So what do you all think? Is it going to be spontaneous or not? I'm thinking it's going to certainly be spontaneous, right? Because all spontaneous processes do what? They increase the entropy of the universe, right? So will this reaction be spontaneous? Yes. Because the entropy of the universe increases. It's a positive number. Let's try a different sample calculation. This one involves computation of our Gibbs free energy change, delta G. Remember, that's called Gibbs free energy change. So for this, we're going to consider a decomposition reaction of carbon tetrachloride. That's the stuff right here. It's going to make graphitic carbon solid and 2 copies of chlorine gas. We're told delta H for this reaction. We're told delta S for this reaction. Delta H is our enthalpy change. Delta S is our entropy change for this reaction. Now what we want to do is compute at 25 degrees Celsius, delta G, determine whether this reaction is spontaneous as written. Let's tackle that one first, okay? So part A. Now this problem, it's kind of user-friendly because we're given values for delta H and delta S. If you're not actually given those in a problem, you may have to actually solve to find them first. Now, we talked about the summation approach last lecture for computing delta S, or the entropy change. You could easily use that summation approach if you're given the reaction. You just have to look up the S0 values, the standard molar entropy values in that table and the appendix at the end of your textbook, and then you can use that summation approach and you're in business, okay? Now, what if you're not given information about the enthalpy? What do you do? Well, it turns out in the same appendix of your book, you can be given the enthalpy of formation values for different substances, and you could use those and an analogous summation rule that you learned about back in chapter 6 to compute the enthalpy change associated with the reaction. Now, if you've forgotten how to do that, I'm going to lead you back to, again, the chapter 6 material. And there's something called Hess's Law, which is outlined on page 275 through 280 of your textbook. 275 through 280. You can look at that and refresh your memory of how to use that summation rule for enthalpy calculations. But in reality, I could have given you only the chemical reaction and ask you to compute this, what we're about to do, and you'd have the ability to do that, okay? But nonetheless, we're happy because we don't have to do that here, and we have a little bit simpler of a problem. So we can jump ahead to the form of our second law of thermodynamics equation for computing our Gibbs free energy change. Delta G is equal to delta H minus T delta S. And this problem is truly plug and chug from here. Let's start with this term out here on the right. We have our delta S. That's our entropy change for the reaction. We're told that that's positive 142.2 joules per degree Kelvin. So we take that number and notice what we do with it. We just plug it into the equation, don't we? Units of joule per Kelvin. Now we're told that this process occurs at 25 degrees. Now that's Celsius. Remember, when we plug into this equation for T, we gotta have Kelvin temperature, so we gotta convert. But easy enough. We just add our 25 to 273, and we've got ourselves the 298. Notice that the sign for entropy comes along for the ride. It was positive here, it's positive down here, okay? So we just plug in the numbers. Now, what about the delta H out in front? This is our enthalpy for our reaction, right? Our enthalpy. Now, we're told up top that the enthalpy of the reaction is 95.7 kilojoules. But is that what we see right there? It's not, right? What we have right here is 95.7, but we multiply by 10 to the 3, or 1,000. And the reason why we did that again is because this unit is kilojoules, isn't it? Down here in the equation, we need to make it joules. The reason why that is to make the units jive with my delta S units. The entropy units, again, typically are joules per Kelvin. But enthalpy, oftentimes it's kilojoules per mole or something similar, something in kilojoules units, right? You gotta have similar units when you're doing your subtraction in this equation. So you gotta convert. That's what they did here in one step by multiplying by 1,000, okay? I just want you to pay attention to that so you don't lose sight of that. It's a very important part of using this equation. But after we do that, we just do the math. We multiply the 298 times the entropy change, the 142.2. We get this number right here, 42.4 times 10 to the third joules. We're going to subtract that from our delta H. They have same units, so we can do the subtraction. And what do we get? We get a positive 53.3 times 10 to the third joules. Notice the units joules. So Gibbs free energy has units of joules, right? Or kilojoules, something like that, but some base unit of joules, right? All right, so we've computed our delta G and found that it was a positive 53.3 times 10 to the third, or 53.3 thousand. Is this a spontaneous process or not at 25 degrees? At 25 degrees Celsius, this reaction is not spontaneous, is it? And how did I know that? There's only one thing I needed to look at, that sign right there. I knew that this reaction was not spontaneous because it was a positive sign for delta G. That tells me the reaction is not spontaneous at this temperature. Now, if I got a negative sign there, then this reaction would be spontaneous, but I didn't. I got a positive sign. This is not spontaneous at 25 degrees. In other words, this carbon tetrachloride is not going to spontaneously decompose to make graphitic carbon and chlorine gas. It's not going to happen at 25 degrees. Now, let's think about what might be possible. Might it be spontaneous at a different temperature? Maybe I heat it up or cool it down, and then the reaction all of a sudden becomes spontaneous because we're operating at a different temperature. Might we be able to predict what temperature this reaction becomes spontaneous? I think maybe we can, and that's going to be the focus of part B for this problem. So what do we notice about the reaction itself if we go back to the beginning, okay? Well, I know that my enthalpy, my delta H, is what? A positive number, isn't it? That's bad for spontaneity. But the good news is that my entropy change is a relatively large positive value at 142.2 joules per Kelvin. And I could certainly predict that from the form of this reaction. Look what's going on. I'm taking one molecule in the gas phase and I'm decomposing it into multiple components. And I get at least 2 moles of gas back. That sounds like I'm increasing the disorder or randomness. I'm increasing the entropy. In fact, I am, right? So this entropy change is a good thing for spontaneity, but I got to overcome this, don't I? I got to overcome this delta H. So how can I do that? Well, let's move on to the next slide in part B. If I go back to the form of my delta G equation, and I plug in my value for my enthalpy change. Now again, that's still a positive number, isn't it? That's bad for spontaneity because it makes my delta G trend more positive. But I might be able to overcome that positive delta H if I could subtract a large enough number. If I can make this T delta S negative enough, I could subtract a number which is bigger than my delta H, and in doing so make my delta G negative and make the reaction spontaneous. So then what's the trick? The trick is my T. If I can make my T a sufficiently large number when I multiply it by my delta S, my 142.2, the product will eventually become big enough to overcome my positive delta H. So functionally, to solve what temperature is required, I set my delta G equal to 0. And then I solve for T. To do that, I would first begin by taking this second term here and moving it over to the left by subtracting it from both sides. And then in doing that, I could solve for T by taking my delta H and dividing by my delta S. And when I do that, I find the key crucial value for T is 673 Kelvin. When T is 673, and I plug that back in there, I multiply that 673 times this 142, and I get a value here for the second term in my equation that offsets my positive delta H. And any temperature above that crucial temperature, this reaction is going to become spontaneous. So interestingly enough, what I've done here is I predicted the temperature at which this reaction will become spontaneous. At low temperatures, room temperature, say a 25-degree case that we considered first, that reaction was not spontaneous. But if you heat stuff up enough, it will become spontaneous. This is an interesting example to me because it actually explains why all substances will decompose if you heat them enough. Okay, because if you have a molecule, say we abbreviate that molecule AB4, something like that. These are not real elements, right? But it's just some molecule. If you heat it up enough, it's going to decompose into its gas phase atoms. And actually, it should be 4B. Oops. If you heat it up enough, it can get it to decompose into a gas phase collection of atoms. And the reason why is because if you think about the delta S for this reaction, it's going to be positive, isn't it? You're making more gas phase products than you started with. So the entropy is always a positive number. Now, does it cost you energy to break the bonds in this molecule? Yes. But if you heat it up enough, the second term in this equation up top, the second term, the entropy term, becomes large enough to overcome the reaction enthalpy. Right, so all substances, if you decompose them enough, will eventually break down into their elements, okay? All right, so another interesting example. All right, so we come to the last slide here for this particular lecture. But what I wanted to do for a second is consider something we've been talking about earlier this semester, and that is chemical equilibrium, the equilibrium state. We learned about these equilibrium constant expressions. We learned to solve for equilibrium concentrations back in chapters 17 and 18. And now we're learning about this Gibbs free energy business, which predicts spontaneity. Now, when we talked about chemical equilibrium, we talked about shifts via this Le Chatelier's principle. The reaction system might shift left, or it might shift right towards the products. We'll learn to predict those shifts, okay? Can we kind of combine these ideas now and think about chemical equilibrium from a perspective of Gibbs free energy, and specifically Gibbs free energy gradients in terms of how the system might flow towards, say, an equilibrium by trying to establish the lowest chemical potential energy, okay? So to help us think about this, I've got this figure from a textbook, okay? It's considering a very specific reaction, and I want to start there to talk about, and then we'll talk about the figure. So in this reaction, we take nitrogen gas, and we react it with 3 copies of hydrogen to make 2 copies of ammonia gas phase reaction. We're also told that the enthalpy of this reaction is a negative 45.8 kilojoules per mole, okay? Now we got this strange looking graph here. Let's see if we can make sense of it. On the y-axis is our indication of our free energy of our system. On the x-axis is sort of like a reaction quotient, if you want to think about it that way. It really is kind of like a reaction quotient scale. On the far right of our y-axis, we've got a lot of products. We're products heavy. This is a Q. And on the far left, we're reactant heavy. Now, right here in the middle, what do we have? We're at our equilibrium point, okay? That's where our system's trying to reach, that equilibrium. So we can be either product heavy or reactant heavy. And what I like about the way they set up this graph is the right corresponds to product heavy, which also corresponds to having more of this ammonia. And the left is reactant heavy, which is, you know, having more of these guys, the nitrogen, hydrogen. So what I'm interested in thinking about is how this chemical system might respond to flow down this free energy gradient depending on whether we're reactant heavy or product heavy. Okay, now we know this reaction is what? Exothermic, isn't it? What do we know about the delta S for this reaction? Well, we're not told anything right now, are we? But maybe we can make some sense of it, what the sign on the delta S might be by just looking at the reaction. So what do we do here? We take 1, 2, 3, 4 moles of gas. And how many do we make? 2 moles of gas. All right? We take 4, we make 2. So what's the sign on our delta S likely to be? It's likely to be negative, isn't it, in the forward direction? So let's think for a second if that's good or bad for spontaneity. That decrease in entropy over the course of this reaction will be bad for our spontaneity. So as we move forward from left to right, entropy is lowered, and that's bad for spontaneity. However, it's a exothermic reaction, and that's good for spontaneity from left to right. So then, kind of what's driving the bus here, okay? So let's start over here, and if we're a reactant heavy case. If we're a reactant heavy case, what that's going to mean is we have too much of our nitrogen hydrogen, too high a concentration of it for our equilibrium. And we're going to slide down the free energy gradient from left to right to establish our equilibrium. But what's the driving force behind that in terms of our delta G equation? Well, under those conditions, the fact that this reaction is exothermic is the driving force. But what about if we're product heavy on the alternate side, the right side? What's our driving force there? Well, if we're product heavy, what's going to happen is we're moving from right to left, aren't we? If we're product heavy, we're going to be taking our ammonia and making some more of these guys. What drives our establishment of equilibrium there? Well, in that case, it's driven by what? Our delta S, or our entropy change. So moving this way is going to be driven by our entropy effect, and moving this way is going to be driven by our enthalpy effect. Okay, so it's actually kind of an interesting way to think about it, I think. As we move towards equilibrium, we kind of slide down this energy gradient to get to that point of low chemical potential energy, all right? All right, well, I think I'm going to draw close to this lecture. Appreciate you.